A ray of sunlight touches a leaf, and in that quiet moment, a chain begins, one that started deep inside the sun thousands of years before the light ever reached Earth. It warms the oceans, stirs the winds, guides the seasons, feeds forests, and helps fill the atmosphere with oxygen. Even the glowing auroras above the poles are part of this ancient connection between a living planet and its star. If this kind of calm, scientific journey brings a little wonder to the day, please leave a like, subscribe for more long-form explorations, and share the video with someone who may enjoy it too. Thank you sincerely for spending this time here. What time is it where this video is playing, and where in the world are these words being heard? A comment with the time and location would be wonderful to read. Now, let the light travel backward to its source, and begin the story of how the sun awakens life on Earth. Long before forests spread across continents, before oceans carry drifting life, and before Earth itself has fully taken shape, a quiet transformation begins inside a cold region of the Milky Way. The material that will become the sun exists first as part of a vast cloud of gas and dust, thin in some places, denser in others, and almost unimaginably dark. Such clouds are known as nebulae. They contain mostly hydrogen, along with helium and traces of heavier elements forged by older generations of stars. For ages, the cloud remained suspended in space, shaped by gravity, radiation, turbulence, and the distant influence of neighboring stars. Then something changes. A disturbance passes through the cloud, perhaps from the shock wave of a nearby stellar explosion, or from the natural motion of the cloud itself. One region begins to collapse. Gravity pulls scattered particles inward, and the collapse slowly gathers speed. What begins as a broad and diffuse patch becomes a tightening center of mass. Matter falls toward that center from every direction. As it falls, it also spins. Even the smallest original rotation becomes more pronounced as the cloud contracts, much as a turning body spins faster when drawn inward. The result is not a simple sphere, but a broad rotating disk with a dense, brightening concentration at its heart. This is the solar nebula, the birthplace of the sun and the planets that will one day circle it. The young sun is not yet a stable star. It is a protostar, an object still being built by infalling material. Gas crashes into the growing center. Pressure rises, and the interior becomes hotter. The heat does not come from fire in the ordinary sense. There is no burning wood, no flame feeding on oxygen. Instead, gravitational energy is being converted into heat as matter is compressed. Each new layer adds weight to the layers below, and the center grows denser under the force of its own gathering mass. Around it, grains of dust collide and cling together inside the disk. Tiny particles become larger clumps. Clumps become rocky bodies, icy fragments, and eventually the earliest building blocks of planets. This same collapse that creates the sun also prepares the raw structure of the solar system. At the center, however, the process moves toward a decisive threshold. The protostar grows until its core becomes hot and compressed enough for hydrogen nuclei to overcome their natural electrical repulsion. Hydrogen is the simplest and most abundant element in the young star. Its nuclei carry positive charge, and under ordinary conditions they resist being forced together. In the deep center of the forming sun, pressure and temperature become so extreme that collisions occur with tremendous energy. Through a process known as nuclear fusion, hydrogen nuclei begin joining through a chain of reactions that ultimately produces helium. A small amount of mass is converted into energy. This moment does not resemble a sudden explosion that quickly fades. It marks the beginning of a long balance. Gravity continues pulling inward, while energy released by fusion creates pressure pushing outward. When these forces settle into a stable opposition, the Sun becomes a main sequence star, a star in the long central stage of its life. The surrounding disk still contains chaos, collisions, and migration, but the system now has a lasting center. The Sun is born about 4.5 billion years ago in a spiral region of the Milky Way often called the Orion Spur. It is one star among hundreds of billions in the galaxy, neither the largest nor the hottest, yet its position and stability make it extraordinary for the worlds around it. The Sun contains nearly all the mass in the solar system. Its gravity dominates the motions of planets, moons, asteroids, and comets. The planets do not circle it because space is empty and still, but because their forward motion and the Sun's inward pull remain locked together. Each world is always falling toward the Sun, and always moving sideways fast enough to miss it. From this balance come the repeating paths called orbits. The young Earth forms within this gravitational order, assembled from rocky material in the inner solar nebula. Its early surface is violent, hot, and frequently struck by debris. Yet even in this unstable beginning, the Sun is already shaping the conditions that will eventually allow life. Its gravity keeps Earth at a distance where liquid water may later persist under the right atmospheric conditions. Its steady output of energy begins to warm the planet. Its light establishes a repeating rhythm as Earth rotates, dividing the surface into day and night. The connection between the Sun and life does not begin with plants or animals. It begins much earlier, with the basic architecture of a system in which a small rocky world can remain in a stable orbit for immense spans of time. The Sun also determines what kinds of materials survive in different parts of the newborn disk. Close to the young star, heat prevents many volatile substances from condensing easily, favoring metals and rock. Farther away, colder conditions allow water, methane, ammonia, and other compounds to freeze into ices. This temperature pattern helps create the contrast between small rocky planets near the Sun and large gas and ice-rich planets beyond them. Earth's composition, its supply of heavy elements, and much of its early water history are tied to this arrangement. The Sun is therefore more than a lamp placed at the center of a finished system. Its formation controls the system's mass, motion, temperature, and chemical geography from the beginning. Yet the newborn Sun is not gentle. Young stars are often more magnetically active than mature ones. The early Sun likely releases stronger streams of charged particles and more frequent bursts of high-energy radiation. These forces strike the young planets and help shape their atmospheres. Worlds with weak gravity may lose gases more easily. Worlds without effective magnetic protection may experience greater atmospheric erosion. Earth survives not because the young solar system is calm, but because several conditions gradually work together. The planet has enough mass to retain an atmosphere, enough internal heat to sustain geological activity, and eventually a magnetic field that helps deflect part of the solar wind. The Sun gives energy, but it also creates hazards. This early relationship also contains a quiet puzzle. The young Sun shines less brightly than it does in the present age, yet geological evidence indicates that liquid water exists on early Earth. The answer is not supplied by sunlight alone. Earth's atmosphere, rich in heat-trapping gases, helps hold warmth near the surface, while volcanic activity, ocean chemistry, and the gradual cycling of carbon alter the climate over immense spans of time. The habitable state of the planet emerges from an interaction rather than a single gift. Solar energy enters the system, but air, water, rock, and the living world eventually determine how that energy moves and how long it remains. Too little retained heat would leave much of the surface frozen. Too much would drive the climate toward conditions hostile to complex chemistry. Earth occupies a changing middle ground. Never perfectly fixed, but stable enough for oceans to endure, the Sun provides the steady source around which these slower planetary controls can operate. The future of life depends on the distance, shielding, chemistry, and resilience of the world receiving that energy. Over time, the chaotic disk clears. Much of its gas is absorbed, blown outward, or locked into planets and smaller bodies. The Sun settles into a steadier phase. From far away it would appear almost unremarkable, a yellow-white star shining among countless others. From Earth, however, its importance is total. Every dawn is connected to fusion in its core. Every ocean current, weather pattern, leaf, and food web depends directly or indirectly on energy that begins within that star. Even fuels buried underground preserve sunlight captured by ancient organisms. The warmth of a resting stone, the movement of air across a plain, and the slow growth of a forest all belong to the same long chain. That chain begins before Earth is habitable, before Earth has oceans, and before Earth has a stable surface. It begins when a dark cloud collapses and gravity gathers scattered matter into a new center of light. The Sun awakens life only much later, but the possibility of that awakening is built into its birth. A cloud becomes a disk becomes a star, and around that star a small world remains, waiting through fire, impact, and cooling for light to become something more than light. Beneath the calm circle seen from Earth, the Sun is arranged as a sequence of regions, each governed by different pressures, temperatures, densities, and forms of motion. Its visible surface gives the impression of a single shining body. But the star is not uniform from center to edge. It is a layered structure held together by gravity and powered from within, with energy passing through one region after another before escaping into space. The deepest layer is the core, a compact central volume containing only a fraction of the Sun's total size, but producing nearly all of its energy. Here, matter is compressed to an extreme density, and the temperature rises to roughly 15 million degrees Celsius. Under these conditions, atoms cannot remain whole. Electrons move freely among bare atomic nuclei, creating plasma, a state of matter shaped strongly by electric and magnetic forces. The core is where fusion takes place. Hydrogen nuclei move rapidly, collide, and occasionally pass close enough for nuclear forces to bind them through a sequence of reactions. The final result is helium, along with energy carried by radiation and tiny particles called neutrinos. Neutrinos interact so weakly with matter that most leave the Sun almost immediately, crossing its layers and travelling into space without resistance. Light behaves very differently. The energy produced in the core begins as high-energy radiation, but it cannot travel outward in a straight path. The solar interior is so dense that photons are repeatedly absorbed, scattered, and released again. Their outward progress becomes a slow wandering through crowded matter. Surrounding the core is the radiative zone, a broad region where energy is carried mainly by this repeated transfer of radiation. Temperatures remain immense, but they gradually decline with distance from the center. A photon may move a short distance before interacting with a charged particle, changing direction and often losing energy. This happens again and again, turning what seems like a simple journey from the core into a process that may take tens of thousands or even hundreds of thousands of years. The exact travel time is uncertain because the path is statistical rather than direct, yet the basic picture remains clear. Energy that begins in the Sun's center is delayed by the density of the layers above it. The light reaching Earth in a few minutes has a much older history inside the star. Within the radiative zone, the Sun rotates in a relatively smooth way compared with its outer layers. The plasma is under such pressure that large rising and sinking motions are limited. Energy therefore moves mainly through radiation rather than through bulk circulation. Near the outer boundary of this zone lies a thin transition region known as the tachocline. It separates the more uniform rotation of the deep interior from the uneven rotation of the layer above. The Sun is not solid, so its equator rotates faster than regions nearer the poles. The resulting shear in and around the tachocline may help stretch, twist, and organize magnetic fields. Much of the Sun's complex magnetic behavior appears to be connected to this hidden boundary, where internal motion changes character. Above it begins the convective zone. Here, the plasma is cooler and less dense than in the deeper interior, though still far hotter than any ordinary material on Earth can endure. Radiation becomes less efficient at moving energy, because the plasma absorbs light more readily. The energy instead begins to travel through convection. Hotter plasma rises toward the surface, carries heat upward, cools, and then sinks again. This motion forms vast circulating cells. Near the visible surface, the pattern appears as granulation, a shifting field of bright centers surrounded by darker edges. Each bright region marks hot plasma rising from below. While the darker boundaries show cooler material descending, these cells are temporary, continually forming and dissolving, so the photosphere seems to boil in slow, restless patterns. This apparent boiling is plasma moving under gravity while transporting energy from the interior. The convective zone reaches the photosphere, the layer commonly described as the Sun's surface. The Sun has no solid ground. The photosphere is the depth from which most visible light escapes. It is only a few hundred kilometers thick, extremely thin compared with the full diameter of the star. Its average temperature is close to 5,500 degrees Celsius. From Earth, the photosphere appears smooth because of distance and brightness, but close observation reveals granules, dark sunspots, bright regions, and constant motion. Sunspots form where intense magnetic fields suppress convection, with less hot plasma rising through these areas. They become cooler than their surroundings and therefore appear dark by contrast. They are not truly black and would still glow strongly in isolation. Their darkness reveals a local interruption in the usual flow of heat. The number and arrangement of sunspots change over a cycle lasting about 11 years. As the Sun approaches a period of stronger activity, sunspots become more numerous. Magnetic fields grow increasingly tangled, and eruptions become more frequent. This cycle is part of a larger magnetic rhythm in which the Sun's global magnetic polarity reverses. One complete return to the original orientation therefore takes about twice the length of the visible sunspot cycle. Above the photosphere lies the chromosphere, a thin and irregular layer named for the reddish light it can show during a total solar eclipse. The chromosphere is difficult to observe against the brightness of the photosphere, but specialized instruments reveal a landscape of jets, arches, and rapidly changing structures. Narrow columns of plasma called spicules rise and fall, carrying material upward at high speed. Magnetic fields guide much of this motion, shaping the plasma into threads and loops. Strangely, the temperature begins to rise with height through the chromosphere. Moving away from the Sun's core would seem to lead only toward cooler regions, yet the outer atmosphere does not follow that simple pattern. After reaching a minimum near the lower chromosphere, the temperature climbs again. This rise becomes even more dramatic in the transition region, a narrow boundary between the chromosphere and the corona. Across a relatively small distance, the temperature increases from tens of thousands of degrees to hundreds of thousands and then millions. The reason for this heating is one of the Sun's long-studied mysteries. The corona, the outermost atmosphere, extends millions of kilometers into space and is far hotter than the visible surface below it. Its plasma is extremely thin, so its total heat content is not comparable to that of the dense interior, but the temperature of individual particles is extraordinarily high. Magnetic waves, small eruptions, and the continual rearrangement of magnetic fields may transfer energy into the corona. Several mechanisms probably act together. The exact balance remains an active area of research. During a total solar eclipse, the corona appears as a pale halo surrounding the darkened disk of the moon. Its shape changes with solar activity. Near quiet periods, it may stretch outward in long streamers concentrated around the sun's equatorial regions. Near active periods, it becomes more complex and spreads in many directions. The corona has no sharp boundary. Its outer material becomes the solar wind, a continuous flow of charged particles through the solar system. In this way, the sun's layered structure opens into interplanetary space. Matter born in the outer atmosphere moves past planets, moons and comets, carrying the influence of solar magnetism far beyond the visible star. Every layer contributes to this outward connection. The core creates energy. The radiative zone delays and transforms it. The convective zone carries it upward through moving plasma. The photosphere releases most of the visible light. The chromosphere and transition region reveal the increasing control of magnetic forces. The corona stretches that influence into space. These regions are not separate shells operating in isolation. They exchange matter, energy, and magnetic stress. A change deep within the sun can eventually alter activity at the surface, while motions near the surface can twist fields that rise into the atmosphere. The star behaves as a connected system, whose parts move at different speeds and in different ways. From Earth, sunlight seems immediate and simple, arriving as warmth across a landscape or brightness across an ocean, inside the sun. The light belongs to a far more intricate path. It begins in a dense central furnace, wanders through a nearly opaque interior, rides rising currents of plasma, and finally escapes from a surface that is not a surface. Beyond that boundary, the sun continues through glowing layers that grow hotter as they become thinner, ending not in emptiness but in a wind that surrounds the planets. The star at the center of the solar system is therefore not a single flame. It is an architecture of pressure, motion, radiation, and magnetism, each layer preserving a different part of the long passage by which hidden fusion becomes daylight. Deep inside the sun, where no beam of visible light can travel freely and no solid surface can exist, the star's long gift to Earth begins with collisions too small to see. The core is a sphere of compressed plasma extending through roughly the innermost quarter of the sun's radius. It contains hydrogen, helium, free electrons, and traces of heavier elements, all held under immense pressure by the weight of the layers above. The temperature reaches about 15 million degrees Celsius, and the density becomes many times greater than that of water. Under these conditions, matter behaves in ways far removed from ordinary experience. Atomic nuclei move at enormous speeds. Electrons drift freely through the plasma, and gravity maintains a crushing inward force. Yet gravity alone does not produce sunlight. It creates the environment in which nuclear fusion can begin. Hydrogen nuclei are single protons, and each carries a positive electric charge, because like charges repel, two protons approaching one another are pushed apart by the electromagnetic force. Even in the sun's core, most collisions do not lead to fusion. The particles strike, scatter, and separate again. Only a small fraction come close enough for another force to take over. At extremely short distances, the strong nuclear force can bind particles together, but reaching that distance is difficult. The average thermal motion of the protons is not sufficient by itself to overcome the full electrical barrier. Fusion becomes possible because the particles do not behave only as tiny classical objects. In quantum physics, a proton is also described by a spread of probability. There is a small chance that two protons can pass through the electrical barrier without crossing it in the ordinary way, a process known as quantum tunneling. This rare event makes the Sun possible. Across the vast number of particles crowded into the core, rare events occur constantly. The dominant sequence is called the proton-proton chain. It begins when two protons approach closely enough to interact. One of them changes into a neutron through the weak nuclear force, producing a nucleus made of one proton and one neutron. This is heavy hydrogen, also called deuterium. The reaction releases a positively charged particle known as a positron and a nearly massless neutrino. The positron soon meets an electron. Matter and antimatter then destroy one another, converting their mass into high-energy radiation. The neutrino, by contrast, scarcely interacts with the surrounding plasma. It travels outward almost at the speed of light, passing through the solar layers and leaving the star within seconds. Most of the energy remains trapped, but the neutrino carries an immediate message from the core. The new deuterium nucleus soon captures another proton and becomes a light form of helium containing two protons and one neutron. This step releases additional energy as a photon. Later, two of these light helium nuclei collide. They combine into a stable helium nucleus with two protons and two neutrons, while two excess protons are returned to the plasma. Across the full chain, 4 hydrogen nuclei are effectively transformed into one helium nucleus. The final helium nucleus has slightly less mass than the original hydrogen nuclei. The missing mass has not vanished. It has become energy according to the relationship between mass and energy described by relativity. The amount lost in each reaction is small, but the Sun contains so much hydrogen and completes so many reactions that the total output is immense. Every second, the core fuses hundreds of millions of tons of hydrogen into helium. Several million tons of mass become energy during that same interval. The Sun is not diminished in any noticeable way from one day to the next, because its total mass is enormous. It has enough core hydrogen to continue its present main sequence life for billions of years. Fusion is sometimes described as burning, but it is not chemical combustion. Ordinary fire rearranges electrons around atoms and releases energy from chemical bonds. Fusion changes the nuclei themselves and releases far more energy from a much smaller amount of material. Oxygen is not required. Flame is not present. The Sun shines because the deepest parts of its plasma are dense and hot enough for nuclear reactions to proceed steadily. Even then, the process is surprisingly slow. A single proton may remain in the core for billions of years before becoming part of a successful fusion reaction. This slowness is essential. If hydrogen fused too easily, the Sun would consume its fuel rapidly and live for only a brief cosmic interval. The weakness of the first reaction in the proton-proton chain limits the rate. It allows the Sun to release energy gradually, giving planets a stable source of light over geological time. Life on Earth depends not only on the power of fusion, but also on its restraint. The Sun's core continually adjusts to preserve this balance. Gravity presses inward, while the hot plasma and radiation create pressure outward. If the core contracts slightly, it becomes hotter and denser, causing fusion to accelerate. The increased energy raises the outward pressure and pushes against further contraction. If the core expands, it cools, fusion slows, and gravity gains strength again. This self-regulating response helps keep the star stable. The Sun changes over time, but it does not flicker wildly from one year to the next. Its deep interior acts as a natural thermostat, preserving a long equilibrium between collapse and expansion. The energy born in fusion does not immediately resemble the gentle visible light falling across Earth. It begins mainly as high-energy photons, including gamma radiation, and as the rapid motion of particles in the plasma. These photons cannot travel directly outward, because the core and surrounding radiative zone are extremely opaque. A photon is absorbed by a charged particle, released again, scattered, and redirected. Its path becomes a random walk rather than a straight escape. During this prolonged passage, the energy is shared and divided among countless particles and photons. By the time it reaches the visible surface, much of it has shifted into lower energy forms, including the visible and infrared radiation that warm Earth. The sunlight crossing the final distance from the sun takes only a little more than 8 minutes to reach the planet, but the energy within it may have spent an immense span wandering through the solar interior. The neutrinos tell a different story, because they leave the core almost immediately. They allow scientists to test whether fusion is occurring as theory predicts. Detectors buried beneath rock, ice, or water search for the rare moments when solar neutrinos interact with matter. Early experiments detected fewer neutrinos than expected, creating a puzzle known as the solar neutrino problem. The solution emerged when evidence showed that neutrinos can change from one type into another while travelling. The sun was producing the expected flow, but the detectors were sensitive to only part of it. This discovery confirmed both the basic model of solar fusion and the strange behaviour of neutrinos themselves. The core therefore becomes a place where astronomy, particle physics, and the conditions for life meet. Its reactions explain the sun's long stability, while its neutrinos reveal properties of matter that cannot be observed through ordinary light. Helium slowly accumulates as hydrogen is consumed. Because helium is heavier than hydrogen, the core's composition and structure gradually change. The sun responds by becoming hotter and more luminous over immense spans of time. The present star is brighter than it was during Earth's earliest history, and it will continue to brighten slowly long before it reaches the red giant stage. This gradual change influences the distant future of Earth's climate, but for now the rate remains slow enough for the planet's atmosphere, oceans, rocks, and living systems to interact with a nearly steady source. On Earth, the energy released by fusion takes on forms that seem entirely separate from the core that created it. It drives photosynthesis in leaves and microscopic plankton. It warms the oceans, moves winds, lifts water into clouds, and powers the cycle of rain and rivers. It is stored in food, wood, and ancient deposits of carbon. Even many forms of energy that appear terrestrial are transformed sunlight. The motion of air, the flow of surface water, and the chemistry of living tissue all trace part of their history back to hydrogen nuclei joining in darkness. The chain begins with probability, pressure, and particles pressed closer than they would ever come under ordinary conditions. It continues through a slow escape across the sun's layered interior and a rapid flight through space. At the end of that passage, energy enters an atmosphere, touches an ocean, or disappears into a living cell. The brightness of day is therefore the final expression of a hidden nuclear process, one governed by rare interactions and sustained by balance. In the sun's center, hydrogen becomes helium, mass becomes energy, and the smallest changes in matter awaken possibilities across an entire world. The energy that begins in the sun's core does not rush outward as a clear beam. It enters a region so dense that light can barely move before being absorbed, redirected, and released again. The journey from fusion to daylight is therefore not a straight flight, but a long, uncertain wandering through plasma. A photon born near the center may travel only a tiny distance before meeting an electron or atomic nucleus. Its direction changes. Its energy may change. It may disappear into matter and be emitted again as a new photon. This process repeats beyond counting, turning the interior of the sun into an almost opaque maze. The energy drifts outward because the center is hotter than the layers above it, yet each step may point in any direction. Some lead toward the surface, others lead sideways or back toward the core. Over immense spans of time, the overall flow still moves outward through countless interactions. The broad region through which this happens is the radiative zone. It begins outside the core and extends through much of the sun's interior. Matter here remains fully ionized, meaning electrons are separated from atomic nuclei, and the density is still extreme. Radiation carries energy from particle to particle, but the transport is slow because the plasma repeatedly blocks and reprocesses the light. The exact travel time cannot be measured directly, and models produce a range of estimates. It may take tens of thousands of years or far longer for energy created in the core to reach the outer layers. The uncertainty leaves the larger truth unchanged. The sunlight arriving at Earth carries energy whose internal history may be older than human civilization by an immense margin. The final trip through space is brief. The hidden trip inside the star is ancient. During this passage, the original energy changes form many times. Fusion produces high-energy radiation, but those first photons do not survive unchanged. Each absorption and re-emission divides and redistributes the energy. Gamma radiation becomes lower-energy radiation. The plasma itself is heated, and particle motion shares in the transport. By the time the energy approaches the visible surface, it has been transformed into a broad spectrum that includes visible light, infrared radiation, ultraviolet radiation, and other wavelengths. What reaches Earth is not preserved from a single fusion reaction. It is the result of a long chain of exchanges within the solar interior. The sun's light is therefore both continuous and collective, assembled from innumerable events rather than traced cleanly to one beginning. Near the outer edge of the radiative zone, the character of the journey changes. The plasma becomes cooler, but its opacity increases because particles can absorb radiation more effectively. Radiation alone can no longer carry the outward energy efficiently. The sun responds through convection. Hot plasma rises. Cooler plasma sinks and energy travels with the moving material. The convective zone is deep, turbulent, and filled with flows on many scales. Large cells may extend across vast distances, while smaller cells appear near the surface as granulation. Rising plasma expands and cools. Sinking plasma becomes compressed and heats again. Through this circulation, energy that has wandered slowly through the radiative zone is carried more directly toward the photosphere. Even here, however, the path is not simple. The plasma twists under the sun's rotation, magnetic fields resist and redirect the motion, and rising columns break into complex patterns before the energy finally reaches a region thin enough for light to escape. At the photosphere, the sun changes from nearly opaque to transparent over a relatively shallow depth. Below this boundary, photons are still likely to be absorbed. Above it, many can travel freely into space. The photosphere is therefore not a solid surface but an optical threshold. It marks the layer from which most visible sunlight begins its final outward journey. The light spreads in every direction across the solar system. Only a very small fraction intersects Earth. Most passes through empty space, warming no planet and entering no living cell. Yet the fraction that reaches Earth is enough to sustain nearly every surface ecosystem and to drive much of the planet's climate. Across the distance between the Sun and Earth, the light travels through near vacuum. Once free of the dense solar plasma, photons move at the speed of light. They cross the average distance in a little more than 8 minutes. Compared with the internal passage, this final stage seems almost instantaneous. The energy may spend ages trapped within the star, then complete the visible part of its journey during the length of a quiet pause. When sunlight reaches Earth, it meets the upper atmosphere first. Some wavelengths are absorbed by gases, some are scattered by molecules and tiny particles. Shorter blue wavelengths scatter more easily than many longer wavelengths, giving the daytime sky its familiar color. During sunrise and sunset, sunlight passes through more atmosphere, and much of the blue light is scattered away from the direct path, leaving stronger reds and oranges. The colors of the sky are not painted onto the atmosphere. They are signs of solar radiation being filtered and redirected during its final approach to the ground. Clouds reflect and scatter light in other ways. Dust, water droplets, ice crystals, smoke, and pollution alter the path again. So the same sunlight can produce soft grey mornings, bright white cloud fields, halos, and deep evening colour. The atmosphere also protects the surface from some of the sun's more energetic radiation. Ozone absorbs much ultraviolet light that would otherwise damage living tissue. Other gases absorb particular bands of infrared and ultraviolet radiation. The atmosphere is neither fully transparent nor fully opaque. It is selective, allowing much visible light through while reshaping the spectrum that reaches the ground. Once sunlight arrives at the surface, its paths multiply. A portion reflects from clouds, ice, water, rock, soil, and living leaves. A portion is absorbed and converted into heat. Dark oceans and forests tend to absorb more than bright snow or ice, creating differences that influence local and global temperature. Warm surfaces transfer heat into the lower atmosphere. Oceans store solar energy and release it slowly. Land warms and cools more quickly. These contrasts help drive winds, storms, currents, and seasonal patterns. The energy that began as mass transformed in the core becomes motion in air and water. It lifts moisture from oceans through evaporation, helps form clouds, and returns water through rain and snow. It powers the circulation that connects tropics, poles, continents, and seas. Some sunlight enters living systems instead. Pigments in plants, algae, and certain microorganisms absorb selected wavelengths. Through photosynthesis, that energy helps convert carbon dioxide and water into energy-rich molecules. The light does not remain light. It becomes chemical potential, stored in bonds and later released through metabolism. Animals obtain that energy by eating plants or by eating organisms that have already consumed them. Decomposers continue the transfer after death. Food webs are therefore pathways through which captured sunlight moves, changes, and fades, even deep beneath the sea, where sunlight never reaches. Many ecosystems still depend indirectly on organic material produced near the surface and carried downward. Some communities rely instead on chemical energy from Earth's interior, but at the planetary scale, sunlight remains the dominant source for life at the surface. The journey also leaves long records. Ancient plants capture solar energy and bury part of it in sediments. Over geological time, heat and pressure transform some of this material into coal, oil, and natural gas. The energy released when these fuels burn is old sunlight returning in altered form. Wood burning in a fire, food fueling a body, wind turning a turbine, and water descending through a dam all belong to different branches of the same solar history. Even the weathering of rock and the movement of soil are influenced by solar-driven rain, ice, roots, and temperature change. The sun's energy spreads so widely through Earth's systems that its original path becomes difficult to recognize. Yet the chain remains unbroken. Fusion creates energy. Radiation carries it outward. Convection lifts it toward the photosphere. Space delivers it to Earth. Atmosphere, ocean, rock, and life transform it again. This long escape is not merely a physical journey from one location to another. It is a sequence of conversions, each one opening a new possibility. High-energy photons become a softer spectrum. Light becomes heat. Heat becomes motion. Light also becomes chemical energy, growth, breath, and decay. The sunrise that appears sudden at the horizon is only the final visible moment in a history that begins deep inside the sun. Beneath that brief arrival lies a hidden age of scattering, absorption, circulation, and release. Daylight seems immediate, but the energy within it has crossed a star before crossing space. Gravity is silent, invisible, and everywhere, yet it gives the solar system its shape. The sun does not hold the planets with a material thread. Its mass curves the space around it, and every planet moves through that curved geometry while carrying its own forward motion. The result is orbit, a continuous fall that never reaches the center. Earth is drawn inward by the sun's gravity, but it also moves sideways fast enough to keep missing the star. This balance repeats moment after moment, producing the long path around the sun that defines the year. The same principle governs the other planets, dwarf planets, moons, asteroids, and comets. Each follows a route shaped by speed, distance, mass, and the influence of nearby bodies. The system appears orderly because gravity binds it, but the order is active rather than still. Every orbit is motion held inside a persistent tension between escape and descent. The Sun dominates this structure because it contains almost all the mass in the solar system. Planets are large compared with human scales, yet together they form only a small fraction of the system's total mass. The Sun's gravitational influence therefore reaches far beyond the visible disk. It controls the paths of worlds close to its heat and the slow movement of icy bodies in the distant dark. Even where sunlight becomes faint, gravity remains strong enough to keep objects connected to the same central star. The system's outer influence fades across vast distances, where the sun's pull meets the gravity of passing stars in the Milky Way. Within that domain, the sun creates a common center around which countless bodies move. Earth's place within this structure is neither accidental nor perfectly fixed. It forms in a disk where material already circles the young sun. Dust grains, rocks, and growing planetary bodies share the inherited motion of the solar nebula. As these objects collide and combine, Earth gains mass while remaining in orbit. The growing planet also changes the paths of nearby material, sweeping some objects into itself, scattering others outward, and trapping some in related orbits. The early solar system is crowded and unstable. Young planets exchange gravitational energy, shift position, and influence one another for immense spans of time. Some bodies collide, others are ejected. Gradually, the surviving planets settle into a more durable arrangement. The present order is the remnant of a long sorting process. Earth's orbit is slightly elliptical rather than perfectly circular. Its distance from the Sun changes during the year, but the change is modest compared with the scale of the orbit itself. The seasons do not arise mainly from this variation. They result from the tilt of Earth's axis, which changes the angle and duration of sunlight across the hemispheres as the planet travels around the Sun. Gravity provides the repeating path on which this seasonal pattern can occur. Without a stable orbit, the rhythm of light and climate would be far more chaotic. Too close to the Sun, Earth would receive much more energy. Too far away, the planet would receive less. Yet distance alone does not determine habitability. Atmosphere, oceans, clouds, surface reflectivity, geology, and chemical cycles all affect temperature. Gravity supplies the framework within which these systems operate. It keeps Earth near a nearly steady source of energy for billions of years, allowing slower processes to shape the surface without the planet drifting rapidly into darkness or heat. The Sun's gravity also keeps Earth moving at a speed suited to its distance. A slower Earth at the same location would fall inward. A much faster one could escape into a wider orbit or leave the solar system. Orbital motion depends on a precise relationship between velocity and gravitational pull, but this precision emerges naturally from the conditions of formation and the laws of motion. Small disturbances occur constantly. The other planets tug on Earth, and Earth tugs on them. Jupiter, with its large mass, produces especially important effects across the solar system. The Moon pulls strongly on Earth as well, raising tides and causing subtle changes in the planet's motion. The orbit shifts and wobbles over long periods, but it remains bounded. These slow variations help alter climate patterns across geological time by changing the shape of Earth's orbit, the tilt of its axis, and the direction in which that axis points. Gravity, therefore, does more than hold Earth near the Sun. Through delicate interactions, it helps modulate the distribution of sunlight across ages. The Moon adds another layer to this stability. It forms early in Earth's history, probably after a vast collision between the young Earth and another planetary body. Debris gathers into a companion that remains gravitationally bound to the planet. The Moon's pull creates tides in the oceans and even slight tides in the solid Earth. Friction associated with these tides gradually slows Earth's rotation, lengthening the day over deep time. The exchange of angular momentum also causes the Moon to move slowly farther away. The Moon helps stabilize the tilt of Earth's axis, limiting extreme changes that might otherwise produce more severe climate variations. Its presence does not guarantee life, but it contributes to the stable rhythms within which life evolves. Gravity binds not only the Sun to Earth, but Earth to the Moon to the oceans, and the oceans to the slow timing of the planet. Asteroids and comets reveal the less settled side of the same force. Many remain in stable belts or distant reservoirs, but gravitational encounters can redirect them. Jupiter may capture, scatter, or disturb smaller bodies. Resonances occur where orbital periods form repeating relationships, allowing small gravitational tugs to accumulate. Some regions become cleared, while others collect objects in stable patterns. A body may remain undisturbed for millions of years and then enter a new path after a close encounter or gradual shift. Earth's history records repeated impacts, some minor and some transformative. Gravity creates the stability that allows life to persist, yet it also delivers material and danger. Water and carbon-rich compounds may arrive partly through impacts during the planet's early history. Later collisions alter ecosystems, climates, and evolutionary paths. Even the Sun itself moves in response to the planets. The solar system does not orbit a perfectly fixed point at the Sun's center. Instead, the Sun and planets move around a shared center of mass known as the barycenter. Because the Sun is overwhelmingly massive, this point usually lies near or within it. Though the large outer planets can shift the barycenter beyond the solar surface, the star therefore performs a subtle motion while governing the larger system. Gravity is mutual. Earth pulls on the Sun just as the Sun pulls on Earth, though Earth's effect is far smaller. Beyond the planets, the Sun's gravity holds comets in distant populations, where orbital periods may span thousands or millions of years. Passing stars and galactic tides can disturb these remote objects, sending some inward. As a comet approaches the Sun, heat releases gas and dust, creating a glowing atmosphere and tails that stream away under the influence of radiation and the solar wind. Yet the comet's long curved path is gravitational. It may swing around the Sun and return to darkness, or it may be altered, broken, captured, or expelled. Gravity writes these paths across distances so great that a single orbit can outlast civilizations. For Earth, the most important result is continuity. The sun rises because Earth rotates, and the seasons return because Earth remains in orbit. Oceans stay attached to the planet because Earth's gravity holds them. The atmosphere remains because the planet is massive enough to retain gases against their thermal motion, though some particles still escape. Mountains, rivers, rain, and living bodies all exist within the same downward pull. Solar gravity builds the larger home, while Earth's gravity shapes the local one. Life depends on both. Too little planetary gravity might allow the atmosphere to thin away. Too much could create very different pressures, landscapes, and biological possibilities. The conditions on Earth emerge from a particular scale of mass inside a larger solar structure. Gravity does not create life by itself, but it creates persistence, and persistence allows complexity to grow. Chemical systems need time. Oceans need time. Climate regulation needs time. Evolution needs spans so long that countless generations can explore new forms. The sun's gravity grants Earth a recurring path through light and darkness, warmth and season, while preventing the planet from wandering freely into interstellar space. It is an invisible restraint, but not a prison. Within it, Earth moves endlessly, carrying oceans, continents, air, and life around a star that anchors the whole system. The home of life is therefore not only a planet, it is an orbit, a balance, and a vast gravitational architecture that keeps a fragile world returning to the light. Earth receives only a tiny fraction of the energy released by the sun, yet that fraction is enough to keep oceans liquid, move the atmosphere, and maintain a surface where life can persist. The planet does not simply absorb sunlight like a dark stone. It reflects part of the incoming radiation, scatters part through clouds and air, stores part in water and soil, and sends part back towards space as heat. Between arrival and escape, solar energy passes through a system of oceans, continents, gases, ice, living organisms, and moving currents. The warmth of Earth is therefore not created by distance alone. It emerges from a balance between the energy received from the sun and the energy the planet eventually loses. That balance shifts from place to place, from season to season, and across geological time, but it remains stable enough for liquid water to endure over immense spans. The sun delivers energy mainly as visible light, along with infrared and ultraviolet radiation. When this energy reaches the upper atmosphere, clouds reflect a large portion back into space. Bright surfaces such as snow, ice, and deserts also reflect strongly. Darker surfaces, especially oceans and forests, absorb more. The fraction reflected by a planet is called its albedo. A high albedo keeps more solar energy from being absorbed, while a low albedo allows greater warming. Earth's overall reflectivity changes as cloud cover, ice, vegetation, dust, and human activity alter the surface and atmosphere. These changes can strengthen or weaken climate patterns. Expanding ice reflects more sunlight and encourages further cooling. Melting ice exposes darker land or water, which absorbs more energy and encourages further warming. Most absorbed solar energy warms the surface. The ground heats the air above it. Oceans store enormous quantities of heat because water can absorb much energy while changing temperature slowly. Land warms quickly during the day and cools quickly at night, while oceans respond more gradually. The contrast helps create breezes, monsoons, storms, and large circulation patterns. Warm tropical waters carry heat toward higher latitudes through ocean currents. Winds move heat through the atmosphere, Without these transfers, regions near the equator would become much hotter, while the poles would become much colder. The planet's fluid systems soften the uneven distribution of sunlight, though they never remove it completely. Earth is a sphere, so sunlight strikes different regions at different angles. Near the equator, rays arrive more directly and concentrate energy over a smaller area. Near the poles, the same amount of light spreads across a broader surface and passes through more atmosphere. The tilted axis adds a yearly rhythm, changing the angle and duration of sunlight in each hemisphere. Day length expands and contracts. Seasonal warmth follows with a delay because land and water require time to heat and cool. Life grows within these patterns. Forests open leaves during favourable months. Plankton blooms when light and nutrients align. Animals migrate, reproduce, rest, or change form according to recurring shifts in temperature and daylight. Climate becomes a timing system driven by Earth's movement through solar light. Yet sunlight alone would not keep the surface as warm as it is. Earth's atmosphere contains gases that absorb some of the infrared radiation emitted by the warmed surface. Water vapour, carbon dioxide, methane, and other gases allow much incoming sunlight to pass through, then slow the escape of heat. This natural greenhouse effect raises the average surface temperature by many degrees and makes widespread liquid water possible. Without it, Earth would be much colder, with oceans largely frozen. Its strength depends on the concentration of heat-trapping gases. When those concentrations change, the balance between incoming sunlight and outgoing heat changes as well. The atmosphere then warms or cools until a new balance is approached. Water vapour plays a powerful role because warmer air can contain more moisture. When warming increases evaporation, additional water vapour can trap more heat, strengthening the original change. Clouds complicate the response. Some reflect sunlight and cool the surface, while others trap infrared radiation and warm it. Their effect depends on height, thickness, location, and droplet size. Earth's climate is therefore a network of feedbacks in which oceans, ice, air, rock, and life respond to one another. The sun provides the energy entering this network, but the planet determines how that energy is stored, moved, and released. Over deep time, geology helps prevent the climate from drifting without limit. Volcanoes release carbon dioxide from Earth's interior. Rainwater combines with carbon dioxide and reacts with exposed rock in a process known as chemical weathering. Rivers carry dissolved materials toward the oceans, where carbon can become locked into sediments and eventually into carbonate rock. Plate tectonics carries some of this material into the planet, while later volcanic activity releases carbon again. This slow carbon cycle acts over millions of years. In warm, wet conditions, weathering tends to accelerate and remove more carbon dioxide from the atmosphere, encouraging cooling. In cold conditions, weathering slows, allowing volcanic carbon dioxide to accumulate and encourage warming. The cycle is imperfect, but it offers a long-term stabilizing influence. It helps explain how Earth remains habitable even as the sun gradually brightens over billions of years. The young sun emits less energy than the modern sun, yet ancient Earth contains liquid oceans, a thicker atmosphere rich in greenhouse gases, along with different cloud behavior, ocean chemistry, land distribution, and volcanic activity. Likely helps resolve this faint young sun problem. The answer lies in the interaction of a dimmer star with a different planet. Earth's early atmosphere contains little free oxygen and far more carbon dioxide and methane than later ages. As life evolves and geology changes, the atmosphere also changes, altering the way solar energy is retained. Habitability is therefore not a fixed zone drawn permanently around the sun. It is a relationship between stellar output and planetary response. Venus and Mars reveal how differently that relationship can develop. Venus receives more sunlight and possesses a dense atmosphere dominated by carbon dioxide. Its powerful greenhouse effect produces surface temperatures hot enough to melt some metals. Mars receives less sunlight and has a thin atmosphere that cannot retain much heat. Liquid water may once have flowed across its surface when the planet was warmer and its atmosphere thicker. But present conditions are cold and dry across most of the world. Earth lies between them in distance, yet its moderate climate also depends on its mass, active geology, oceans, magnetic environment, atmospheric history, and living systems. Liquid water is central because it connects climate, chemistry, and life. Water absorbs and transports heat, dissolves minerals, carries nutrients, shapes landscapes, and provides the medium in which the earliest known life develops. Its three common states move continuously through the climate system. Sunlight evaporates water from oceans, lakes, soil, and living surfaces. Cooling air condenses vapor into clouds. Rain and snow return water to the ground. Rivers carry it toward the sea, while ice stores it for years or millennia. This cycle distributes both matter and energy. Evaporation cools surfaces by carrying away heat. Condensation releases that heat into the atmosphere, helping power storms. A drop of rain belongs to a planetary circulation whose engine is sunlight. The warmth that supports life is therefore dynamic. It does not mean that Earth remains uniformly mild. The planet passes through ice ages, warm greenhouse intervals, abrupt climate shifts, volcanic winters, and periods of biological crisis. Continents move, ocean gateways open and close, mountain ranges rise, and atmospheric composition changes. The sun's energy remains broadly steady across human timescales, but the planetary response continually evolves. Life survives by adapting to this changing field of heat and light. Microorganisms persist beneath ice, in hot springs, inside rock, and near deep ocean vents. Complex ecosystems spread where energy, water, and nutrients remain available. The habitable Earth is not free of extremes. It is a world where enough regions remain suitable for long enough that life can continue, diversify, and reshape the environment. Every warm current, cloud field, and green landscape belongs to the same exchange. Solar radiation enters from above. Earth absorbs, reflects, stores, and releases it. The atmosphere slows the loss of heat. Oceans move warmth across the globe. Rocks and living systems alter the gases that regulate the balance. Through this continuing negotiation, a small planet avoids becoming permanently frozen or endlessly overheated. The sun awakens life not by holding Earth at one perfect temperature, but by supplying a steady flow of energy that the planet can transform. Warmth becomes circulation, evaporation, weather, chemistry, and shelter. It keeps water moving and allows molecules to meet, react, separate, and meet again. Between the cold of space and the fire of the star, Earth maintains a narrow, restless climate in which oceans remain open and life has time to grow. Light reaching Earth does not remain only as warmth. In countless living cells, a small part of it is captured and redirected into chemistry. This process, photosynthesis, allows certain organisms to use the energy of sunlight to build energy-rich molecules from carbon dioxide and water. Plants perform it in leaves and stems. Algae perform it in oceans, lakes, and damp surfaces. Cyanobacteria, among the oldest known groups of photosynthetic organisms, perform it across waters, soils, and microbial communities. Together, these organisms form the main gateway through which solar energy enters the living world. Nearly every forest, grassland, coral reef, and open ocean food web depends on this conversion, whether the connection to sunlight is immediate or separated by many steps. The process begins with pigments, molecules that absorb particular wavelengths of light. Chlorophyll is the best known. It absorbs strongly in the red and blue parts of the visible spectrum while reflecting more green light, giving many leaves their familiar colour. Other pigments absorb different wavelengths and help organisms use light under varied conditions. In the shaded depths beneath a forest canopy, in clear surface waters, or within dim layers of the sea, the available colours change. Photosynthetic life responds with different combinations of pigments, adjusting the range of solar energy it can collect. A leaf is therefore not simply a flat green surface. It is a carefully organised structure that guides light, air, water, and chemical reactions into close contact. Within plant cells are chloroplasts, small compartments where photosynthesis occurs. Their internal membranes are folded into flattened sacs called thylakoids. Embedded in these membranes are clusters of pigments and proteins known as photosystems. When a photon strikes a pigment, its energy can excite an electron, raising that electron into a more energetic state. The energy then moves through neighbouring pigment molecules until it reaches a reaction centre. There, an electron is transferred into a chain of carriers. Light has begun to become electrical and chemical energy. This first stage does not directly build sugar. It creates the temporary forms of energy needed for the later work. Water supplies replacement electrons. In one of the most consequential reactions in Earth's history, water molecules are split. Electrons enter the photosynthetic machinery. Hydrogen ions help create an energy gradient, and oxygen is released as a byproduct. The oxygen moving from a leaf into the air is therefore derived from water rather than from carbon dioxide. The reaction requires energy, and sunlight provides it. The freed electrons move through a transport chain across the thylakoid membrane. Their passage helps pump hydrogen ions to one side, creating an imbalance. The ions then flow back through a molecular structure known as ATP synthase. Like a microscopic rotary machine, it uses the flow to produce ATP, a molecule that stores usable chemical energy. Another carrier molecule receives energized electrons and hydrogen, creating reducing power for later reactions. At the end of the light-dependent stage, the cell has converted incoming radiation into compact chemical forms. These products move into the surrounding region of the chloroplast, where the second broad stage begins. Carbon dioxide enters plant leaves through tiny adjustable openings called stomata. These pores allow gas exchange, but they also permit water vapour to escape. A plant must therefore balance the need for carbon with the risk of drying. Inside the chloroplast, carbon dioxide enters a cycle of enzyme-guided reactions. The most important entry step is controlled by an enzyme called rubisco, which attaches carbon dioxide to an existing carbon-based molecule. The resulting compound quickly divides and passes through further reactions powered by the ATP and reducing molecules created from light. Eventually, some carbon leaves the cycle in the form of small energy-rich molecules that can be assembled into sugars and many other compounds. The cycle then rebuilds its starting material and continues. Photosynthesis is often summarized as carbon dioxide and water, becoming sugar and oxygen. But the real process is a network of reactions, transfers, and temporary molecules. Its importance lies in the direction of energy. Light arrives in a form that cannot be eaten, stored in a root, or used directly to build muscle and bone. Photosynthetic organisms convert it into chemical bonds. Those bonds can persist after sunset, move through tissues, and pass from one organism to another. A plant may use newly captured energy to grow a leaf, extend a root, produce a seed, repair damage, or store starch. An animal eating that plant breaks down some of the molecules through cellular respiration, releasing usable energy. A predator eating the animal continues the transfer. Fungi and bacteria decompose remains and wastes, returning nutrients to soil and water while using part of the stored energy themselves. At each step, some energy becomes heat and spreads into the environment. Matter cycles, but energy flows. It enters mainly as sunlight and eventually leaves Earth as infrared radiation. The living world occupies a temporary passage within that flow. On land, leaves form immense surfaces for capturing light. A forest canopy spreads across layers, with sunlit crowns above and shade-adapted plants below. Grasses arrange narrow leaves to survive wind, drought, grazing, and changing light. Desert plants reduce water loss through thick tissues, protective coatings, and specialized forms of carbon capture. Some open their stomata mainly at night, storing carbon for use during the day when light is available but the pores remain closed. These adaptations reveal that photosynthesis is limited not only by sunlight, water, temperature, carbon dioxide, nutrients, and leaf structure all influence its rate. Too little light slows energy capture. Too much can damage the photosynthetic machinery unless excess energy is safely released. Life does not merely accept sunlight, it regulates, filters, and survives it. In the oceans, microscopic phytoplankton perform a vast share of global photosynthesis. These drifting organisms include cyanobacteria, algae, and other forms that live mostly in the sunlit upper layer. They may be invisible individually, but together they support marine food webs and influence the atmosphere. Tiny grazers consume them. Fish consume the grazers. Larger animals depend on the chain. When plankton die or release material, some carbon sinks into deeper water, where it may be consumed, recycled, or buried in sediment. The ocean therefore absorbs sunlight through living cells and redistributes part of its chemical result into darkness. Even creatures that never approach the surface may depend on carbon first fixed in light far above. Some deep-sea ecosystems instead use chemical energy released from Earth's interior, showing that life can begin food webs without sunlight. Yet these chemosynthetic communities remain exceptions within the modern global biosphere. Across most of Earth's surface, sunlight is the primary energy source. The daily rhythm of photosynthesis follows the turning planet. At dawn, light activates the photosystems. As brightness increases, carbon fixation accelerates until other limits become important. Heat may force stomata to narrow. Dry air may increase water loss. Clouds may reduce light. At night, photosynthesis stops. But respiration continues as cells use stored molecules to maintain life. Across seasons, plants alter leaf number, pigment, growth, and dormancy. In the ocean, blooms appear when sunlight, nutrients, and stable waters align. Satellite instruments can detect changes in reflected color, revealing broad patterns of chlorophyll across continents and seas. From space, life leaves a faint spectral sign because pigments absorb and reflect light selectively. This connection between starlight and living chemistry also reaches into Earth's past. Before complex plants exist, photosynthetic microbes are already capturing solar energy. Some forms of early photosynthesis do not release oxygen, using other substances in place of water. Later, cyanobacteria develop oxygen-producing photosynthesis, opening a transformation that will alter oceans, rocks, atmosphere, and evolution. The reaction inside a microscopic cell begins to change the entire planet. Yet the immediate purpose is not planetary engineering. Each organism captures energy to persist, grow, and reproduce. The global consequences emerge from accumulation across countless generations. Every blade of grass and drifting photosynthetic cell continues this ancient exchange. Photons leave the sun, cross space, enter pigments, and raise electrons into motion. The energy becomes ATP, carbon compounds, wood, fruit, plankton, tissue, and breath. It passes through feeding, growth, decay, and renewal before dispersing as heat. Life does not create energy. It receives a flow and builds temporary order within it. Through photosynthesis, the sun's distant fusion becomes the close chemistry of a living cell, and light becomes something that can root, swim, bloom, and feed a world. For much of Earth's early history, the atmosphere contains almost no free oxygen. The young planet is active, volcanic, and chemically restless. Gases rise from the interior, oceans gather across the surface, and sunlight reaches a world inhabited only by simple microorganisms. Life already uses chemical pathways to survive, but the air and water remain unlike those of the present day. Oxygen is present inside compounds such as water and carbon dioxide. Yet very little exists as a separate gas. That changes when certain microorganisms begin using sunlight to split water during photosynthesis. The reaction allows them to build organic matter while releasing oxygen as a byproduct. At first, the effect is local and easily hidden. The new gas does not immediately fill the atmosphere. It reacts with the world around it. Dissolved metals in the oceans absorb it. Volcanic gases consume it. Fresh rock and seafloor material bind with it. The first oxygen disappears into chemical sinks almost as quickly as it's produced. Still, generation after generation, photosynthetic microbes continue. Their individual cells are microscopic, but their combined influence extends across seas and shallow coastal environments. Cyanobacteria form mats in sunlit water, growing in layered communities that trap sediment and build structures known as stromatolites. Some of these formations survive in ancient rock, preserving evidence that sunlight-driven life is already shaping the planet billions of years ago. The organisms do not act with any global purpose. They seek energy, carbon, and survival. Yet the chemistry of their metabolism alters the environment around them. Oxygen is highly reactive. When it meets iron dissolved in seawater, the iron oxidizes and becomes less soluble. It settles toward the seafloor as iron-rich minerals. Over time, repeated episodes create broad layers called banded iron formations, in which iron-bearing bands alternate with other sediments. These ancient deposits record an ocean gradually encountering oxygen. They also reveal why the atmosphere remains oxygen-poor for so long. The planet contains enormous reservoirs of reduced material, substances able to react with oxygen and remove it from circulation. Before oxygen can accumulate in air, many of these reservoirs must become altered or filled. The transition unfolds slowly, unevenly, and in pulses. Different regions of the ocean may contain different amounts. Sunlit surface waters near microbial communities can become oxygenated, while deeper waters remain anoxic, meaning they lack free oxygen. Local changes appear long before a global shift. Eventually, however, oxygen production begins to exceed the capacity of the old sinks. More oxidized minerals form. Methane in the atmosphere reacts and declines. Oxygen starts to persist for longer periods and spread more widely. This broad transformation, commonly called the Great Oxidation Event, begins more than 2 billion years ago. It is not a single moment when the sky suddenly changes. It is a prolonged planetary transition marked by rises, falls, and uncertain intervals. Geological evidence records the disappearance of minerals that cannot survive exposure to oxygen. the appearance of oxidized soils and sediments, and changes in sulfur chemistry. Together, these signs indicate that free oxygen becomes a lasting part of the atmosphere. For many organisms alive at the time, this gas is not a blessing. Oxygen can damage cells by producing highly reactive molecules that attack proteins, membranes, and genetic material. Life adapted to oxygen-free conditions faces a new chemical threat. Some organisms retreat into sediments, stagnant waters, deep subsurface environments, and other places where oxygen remains scarce. Others evolve protective enzymes and repair systems. A few begin to use oxygen itself. This becomes one of the most important biological opportunities created by the change. Oxygen allows a highly efficient form of cellular respiration. Instead of extracting only a small amount of usable energy from food molecules, cells can release far more by transferring electrons through oxygen-dependent pathways. The chemistry supports greater activity, larger genomes, more complex internal structures, and eventually larger bodies. Oxygen does not automatically create complexity, and complex life does not appear at once. Many other conditions matter, including nutrient supply, ecological interaction, climate stability, and evolutionary innovation. Yet oxygen expands the amount of energy available to organisms, widening the range of possible forms. The atmosphere also changes the way sunlight reaches the surface. In the upper atmosphere, oxygen molecules are split and recombined through reactions driven by ultraviolet radiation. Some form ozone, a molecule made of 3 oxygen atoms. Ozone absorbs much of the sun's harmful ultraviolet radiation before it reaches the ground. Early life in water already has some protection because water absorbs and scatters damaging wavelengths. A stronger ozone layer gradually makes exposed surfaces less hostile. Much later, this protection helps life move into shallow water, damp shorelines, and eventually onto land. The same element released by microscopic cells therefore alters both metabolism and planetary shielding. Oxygen also changes the colors and chemistry of Earth. Iron-rich rocks weather into red and brown minerals. Soils develop new forms. The oceans begin to separate into oxygenated upper layers and deeper low oxygen zones, though the pattern shifts repeatedly over time. Nutrients such as phosphorus move differently under changing redox conditions. The chemical balance between oxidized and reduced states. These nutrient changes influence productivity, which in turn affects oxygen production. A feedback develops between life and environment. Photosynthetic organisms release oxygen. Oxygen changes ocean chemistry. Ocean chemistry controls nutrient availability. Nutrients limit or support further photosynthesis. The planet becomes a connected system in which biology and geology continually modify one another. Oxygen levels remain far below modern values for much of the time after the first major rise. The early increase is only the beginning. For more than 1 billion years, Earth may remain in a middle state, with oxygen present in the atmosphere and surface ocean, but limited in deeper waters. Complex cells, known as eukaryotes, emerge within this changing world. These cells contain internal compartments, including a nucleus and energy-producing structures called mitochondria. Mitochondria descend from bacteria that once lived independently, and later formed a lasting partnership inside another cell. They use oxygen to release energy efficiently from organic molecules. This internal alliance becomes a foundation for animals, plants, fungi, and many single-celled organisms. The oxygen produced outside the cell and the oxygen used inside it become parts of the same planetary cycle. Later rises in oxygen coincide with major biological transitions, though the exact causes and timing remain debated. Larger and more active organisms require reliable energy. Multicellular bodies also face the challenge of moving oxygen from the environment into internal tissues. Early animals evolve shapes thin enough for diffusion, then later develop circulatory systems, gills, lungs, blood pigments, and branching networks that deliver oxygen across larger bodies. The availability of the gas does not determine every evolutionary step, but it sets limits on size, activity, and habitat. When oxygen expands into deeper waters, new ecological spaces open. When it declines, marine environments can become stressed or deadly. Earth's history contains repeated anoxic events in which large regions of the ocean lose oxygen, often during intervals of warming, altered circulation, and high nutrient input. These episodes remind the planet that oxygenation is not permanent. It depends on a balance between production, burial, respiration, decay, and geological reactions. Photosynthesis adds oxygen when organic carbon is produced. Respiration and decomposition consume oxygen as organisms break that carbon down. For oxygen to accumulate over long periods, some organic matter must escape rapid decay and become buried in sediment. Carbon burial leaves part of the released oxygen behind. Tectonics, erosion, volcanism, and the formation of mountains all influence how much carbon and nutrient material move through the system. The oxygen in the atmosphere is therefore linked not only to living leaves and cells, but also to sedimentary basins, weathering rock, ocean circulation, and the slow movement of continents. Modern oxygen is maintained by a vast exchange. Plants and algae release it. Animals, plants, fungi, and microorganisms consume it. Fires consume it. Oxidation of rock consumes it. Yet the atmospheric reservoir is large enough that short-term changes remain small. Every breath belongs to a cycle established by ancient microbes and sustained by present ecosystems. The oxygen entering an animal's lungs supports reactions in mitochondria, where food molecules ultimately release energy that began as sunlight. The carbon dioxide leaving the body may later enter a leaf or plankton cell and return to organic form. Light, air, food, and breath are joined in a continuous planetary metabolism. This transformation begins quietly in shallow water, where small organisms capture photons and split molecules of water. Their waste gas first stains the oceans with iron minerals, then enters the atmosphere, changes the sky's chemistry, builds an ultraviolet shield, and supports new ways of using energy. The sun does not place oxygen directly into Earth's air. It supplies the energy that allows life to free oxygen from water and reshape the planet from within. Through countless cells working without awareness of the future, sunlight becomes atmosphere, and atmosphere becomes a new field of possibility for life. Earth's seasons begin with a quiet tilt. The planet's axis is not upright compared with the plane of its orbit around the Sun. It leans by a little more than 23 degrees, and that inclination changes how sunlight reaches each hemisphere during the year. As Earth travels around the Sun, one hemisphere tilts more directly toward the star while the other tilts away. 6 months later, their positions reverse. The result is not a change in the Sun itself, nor mainly a change in the Earth's distance from it, but a repeating shift in the angle and duration of daylight. When sunlight arrives more directly, its energy is concentrated across a smaller area. Days also grow longer, allowing the surface more time to warm. When sunlight arrives at a lower angle, the same energy spreads across a wider area, and shorter days reduce the time available for heating. From this simple geometry comes the seasonal pulse of the planet. Near the equator, day length and solar angle change only modestly through the year. Seasons there are often expressed less through temperature than through rainfall, wind, and the movement of tropical convergence zones. Farther from the equator, the changes become stronger. Temperate regions pass through broad cycles of warming and cooling. Near the poles, daylight can last for months in summer and disappear for months in winter. The same star shines on all these places, yet Earth's tilted orientation divides its energy unevenly across latitude and time. Life evolves within this uneven rhythm. Plants respond to day length, temperature, moisture, and the timing of snowmelt. Animals respond to food, light, heat, and inherited biological clocks. Ecosystems become synchronized with the orbit of the planet. In spring, increasing light stimulates buds, leaves, insects, nesting, and migration. In summer, long days support rapid growth and reproduction. In autumn, declining light and falling temperature trigger seed production, migration, food storage, and dormancy. In winter, many organisms slow, hide, migrate, or survive in resistant forms. These changes do not happen because life understands the sky. They happen because natural selection favors organisms able to anticipate recurring conditions. Day length is especially reliable. Temperature can vary unpredictably from one week to another, but the seasonal pattern of daylight returns with great regularity. Many plants measure the length of night through light-sensitive proteins. When nights become short enough or long enough, depending on the species, flowering begins. This prevents some plants from opening flowers too early, before pollinators appear or before the danger of frost has passed. Other species use a required period of winter cold as part of the signal, ensuring that a brief warm interval does not awaken growth prematurely. The seasonal clock is therefore built from several cues working together. Sunlight provides the stable calendar, while temperature and moisture refine the timing. Trees in temperate forests reveal the cycle in their leaves. During spring and summer, leaves spread broad surfaces toward the light and capture energy through photosynthesis. As autumn approaches, shorter days and cooler conditions change plant hormones. Chlorophyll breaks down, revealing yellow and orange pigments that were present but hidden. Some leaves also produce red pigments as sugars become trapped during the shutdown process. The tree withdraws useful nutrients before sealing the leaf stem. The leaves fall, reducing water loss and preventing damage during winter. Growth continues in a quieter form inside buds, roots, and living tissues protected beneath bark. The apparent stillness of a winter forest is not death. It is a strategy shaped by the seasonal return of light in grasslands. The timing is different but equally precise. Growth may follow rain more than temperature, especially in tropical regions. Grasses rapidly turn available sunlight and water into leaves, seeds, and underground reserves. Grazing animals follow the new growth. Predators follow the herds. When dry conditions return, grasses become dormant above ground while roots remain alive below. Fire may move through the landscape, recycling nutrients and clearing accumulated material. Many grasses survive because their growth points remain protected near or beneath the soil. The seasonal pulse therefore influences not only individual organisms, but entire chains of movement, feeding, reproduction, and disturbance. In the oceans, the cycle is less visible from land but no less important. At high and middle latitudes, winter winds mix surface water with deeper layers, bringing nutrients upward. When spring sunlight strengthens and surface waters become more stable, phytoplankton multiply rapidly. These blooms support zooplankton, fish larvae, seabirds, and larger marine animals. The timing can be brief. If grazers emerge too early or too late, they may miss the period of greatest food. Whales travel enormous distances, feed where seasonal productivity becomes concentrated. Seabirds return to nesting sites when fish and plankton are most abundant. A change in the timing of ice melt, warming, or nutrient supply can separate events that once occurred together. Life depends not only on the amount of solar energy, but on when it arrives relative to other parts of the system. Migration is one of the most visible responses. Birds move between breeding and wintering grounds, guided by changes in daylight, magnetic cues, stars, landscapes, and learned routes. Some insects travel across continents in several generations. Caribou follow the emergence of vegetation and the retreat of snow. Marine animals cross ocean basins between feeding and breeding regions. These journeys are expensive and dangerous, but they allow organisms to use seasonal abundance across different places. The planet's tilt creates regions where food appears in great quantities for a limited time. Migration becomes a way of moving with that temporary wealth. Dormancy offers another solution. Seeds wait in soil through cold or drought. Insects survive as eggs, larvae, or pupae. Mammals enter hibernation or shorter periods of lowered activity. Amphibians bury themselves in mud. Microorganisms form resistant spores. These states reduce energy use until favorable conditions return. The sun remains the distant clock behind the waiting. Even in darkness beneath snow or soil, organisms carry internal rhythms shaped by the expected return of warmth and light. Daily and seasonal clocks often interact. Circadian rhythms organize activity across roughly one day, while annual rhythms guide reproduction, migration, coat changes, and dormancy. Both are adjusted by light. Specialized cells detect dawn, dusk, and day length, then influence hormones and behavior. In many species, the body begins preparing for a season before the weather fully changes. Fur thickens, feathers molt, fat accumulates, or reproductive organs develop in response to changing light. This anticipation is essential because a sudden response may come too late. Seasonal life is built not only on reaction but on prediction. The seasonal pattern itself changes slowly over longer spans. Earth's orbit is influenced by the gravity of other planets, while the tilt and direction of its axis vary through cycles lasting thousands of years. These changes alter how sunlight is distributed by season and latitude. They help pace the advance and retreat of ice sheets during glacial cycles. A cooler summer in high northern latitudes may allow winter snow to survive, increasing reflection and encouraging further cooling. A warmer summer may melt more ice and reverse the trend. The total annual sunlight received by Earth changes far less than its seasonal distribution, yet that redistribution can help transform climate when amplified by ice, oceans, greenhouse gases, and vegetation. Seasons therefore operate on more than one scale. They turn leaves and guide migrations each year, but their long variations also influence the rise and fall of ice ages. Life responds to both the repeating calendar and the slow drift of the calendar's intensity. Species adapt to patterns that appear stable across generations, while evolution continues as those patterns shift. A plant flowering at the wrong time may fail to reproduce. An animal arriving after its food peak may leave fewer young. Over time, populations adjust, move, or disappear. The sun supplies the signal, but the meaning of that signal depends on place, climate, and the network of other organisms. A longer day can awaken one species, release another from dormancy, and begin a chain that spreads through an ecosystem. The seasonal clock is therefore not a single rhythm, but many rhythms layered together. Light reaches soil, leaf, eye, feather, ocean surface, and frozen ground. Each receives the same astronomical pattern through a different biological mechanism. Across Earth, life rises and rests in response to a planet leaning through space. The orbit repeats, the angle of sunlight changes, and living systems answer with bloom, movement, storage, sleep, and return. In this way, the sun awakens life not only once at dawn, but again and again across the year, turning celestial geometry into the timing of growth. The sun's influence does not end where its visible surface fades, beyond the photosphere, chromosphere, and corona. The star continues through magnetic fields and streams of charged particles that fill the space between planets. This extended environment is shaped by the solar wind, a continuous outflow of plasma from the corona. The wind carries electrons, protons, and traces of heavier ions outward at hundreds of kilometers per second. It moves past Mercury, Venus, Earth, and the outer planets, spreading solar material across an enormous volume. Because the particles are electrically charged, they drag part of the sun's magnetic field outward with them, creating a vast structure known as the heliosphere. The heliosphere is not a rigid shell, it is a changing region of solar influence, inflated by the pressure of the solar wind and shaped by the sun's motion through the thin gas between stars. The source of this magnetic reach lies in the motion of plasma inside the sun. The star is not solid, so different parts rotate at different rates. The equator turns faster than regions closer to the poles. Beneath the surface, convection carries hot plasma upward and cooler plasma downward, while deeper layers rotate more evenly. These motions stretch, twist, and fold magnetic fields. Electric currents arise within the moving plasma, and together they operate as a natural dynamo. The solar magnetic field is restless, tangled, and constantly reorganized. Over a cycle lasting about 11 years, the visible signs of activity rise and fall. Sunspots become more numerous, eruptions become more frequent, and the large-scale magnetic field eventually reverses direction. Sunspots are among the clearest marks of this hidden process. They appear dark because they are cooler than the surrounding photosphere, though they remain intensely hot. Strong magnetic fields suppress the normal upward flow of heat in these regions, reducing convection and allowing the surface to cool slightly. Sunspots often appear in groups, with magnetic field lines connecting areas of opposite polarity. The spots change shape, divide, merge, and disappear as magnetic structures rise through the surface and decay. Their number reveals the phase of the solar cycle, while their arrangement hints at tension building in the magnetic field. Magnetic field lines are not physical chords, yet they provide a useful way to describe direction and strength. In the solar atmosphere, plasma tends to move along these lines. Vast arches become visible because hot charged particles are trapped and guided within them. The field can store energy as it is twisted by rotation and convection. When the configuration becomes unstable, it may rapidly rearrange through a process called magnetic reconnection. Field lines break and reconnect in a new pattern, releasing stored energy into heat, radiation, and particle acceleration. This sudden release powers solar flares. A flare can brighten part of the solar atmosphere across a broad range of wavelengths, from visible light to ultraviolet and X-rays. High-energy radiation reaches Earth at the speed of light, so its effect begins only minutes after the eruption. The radiation can alter the upper atmosphere, disturb radio communication, and increase ionization on the sunlit side of the planet. Some release immense amounts of energy in a short interval. A flare does not necessarily send a large mass of solar material toward Earth, but it may occur alongside a coronal mass ejection. A coronal mass ejection is a vast eruption of magnetized plasma from the sun's outer atmosphere. Billions of tons of material can be thrown into space, enclosed within a moving magnetic structure. The eruption expands as it travels, and its path may be directed away from Earth or toward it if it crosses Earth's orbit. The time of arrival depends on its speed and the conditions in the solar wind ahead. Fast events may reach the planet within a few days. The most important factor is not only whether the material arrives, but how its magnetic field is oriented. When the incoming field opposes part of Earth's magnetic field, the two can reconnect more efficiently, allowing energy and particles to enter the planet's magnetic environment. The quiet solar wind also varies. Some regions of the corona are less dense and appear darker in ultraviolet and X-ray observations. These coronal holes contain magnetic field lines that open outward rather than closing back onto the Sun. Plasma escapes along them more easily, creating streams of faster solar wind. As the Sun rotates, these streams sweep through the solar system and may repeatedly reach Earth. Slower solar wind often emerges near the boundaries of more complex magnetic structures, where fast and slow streams meet. They compress one another and create disturbances that can affect planets over repeated rotations. The solar wind therefore carries the pattern of the Sun's changing surface into interplanetary space. Rotation adds a spiral form to this magnetic reach. As the Sun turns, the outward flowing wind draws magnetic field lines into curves, rather like water from a rotating sprinkler tracing a spiral across the ground. This shape is known as the Parker spiral. Near the Sun, the field points more directly outward. Farther away, the spiral becomes increasingly wound. Charged particles moving through the heliosphere follow and scatter along this structure. Energetic particles released by eruptions can therefore reach places that are not directly in a straight line from the source. The magnetic connection between a planet and an active region on the Sun influences when particles arrive and how intense their effects become. The heliosphere also changes over the solar cycle during quieter years. The Sun's large-scale magnetic field is more ordered, and the boundary between magnetic polarities forms a relatively flat structure called the heliospheric current sheet. As activity rises, the sheet becomes warped and rippled. It extends through the solar system like an enormous rotating surface separating regions where the magnetic field points in opposite directions. Planets repeatedly cross this wavy boundary as they orbit. The crossings are usually not dramatic at the surface, but they reveal that interplanetary space is divided by a structure generated at the Sun and carried outward by the wind. Far beyond the planets, the solar wind begins to weaken against the surrounding interstellar medium. The flow slows at a region known as the termination shock. Beyond lies the heliosheath, a turbulent outer zone in which solar material continues to press against the environment between stars. The heliopause marks the broad boundary where the outward pressure of the solar wind is balanced by the interstellar medium. It shifts with solar activity and may be shaped by the direction of the Sun's movement through the galaxy. Spacecraft traveling beyond the major planets have crossed into this distant region, detecting changes in particles and magnetic conditions that reveal the transition from solar space toward interstellar space. The heliosphere offers partial protection to the planetary system. It deflects and modulates some high-energy particles arriving from the galaxy, known as galactic cosmic rays. These particles are not completely blocked, and their intensity near Earth changes with solar activity. During periods of stronger solar magnetism, fewer galactic cosmic rays tend to reach the inner solar system. During quieter periods, more can enter. The relationship is complex because the Sun also produces energetic particles during eruptions. Its magnetic reach therefore shields and disturbs at the same time. For Earth, the consequences depend greatly on the planet's own magnetic field and atmosphere. The solar wind encounters the magnetosphere, compressing it on the day side and stretching it into a long tail on the night side. Most charged particles are diverted around this magnetic obstacle. Some become trapped, some enter through regions near the poles, and some transfer energy during magnetic reconnection. The resulting disturbances can produce auroras, currents in the upper atmosphere, and changes in near-Earth space. Modern satellites, navigation systems, radio links, and electrical networks operate within this changing environment. Life at the surface is protected by layers of distance, magnetism, and atmosphere. But technological systems extend into regions where solar activity becomes more direct. The sun's magnetic influence is therefore both ancient and newly important. Long before technology, it helps shape planetary atmospheres, comet tails, and radiation conditions. In the present age, its changes are measured because invisible storms can affect systems spread across Earth and orbit. Yet even during its strongest activity, the sun remains governed by cycles rather than intention. Plasma rises, rotation twists, fields store energy, and reconnection releases it. From a dark sunspot to the distant heliopause, the same magnetic processes connect the visible star with the space around every planet. The sun awakens life through light and warmth, but it also surrounds that life with an unseen, moving field, a vast extension of the star that reaches far beyond daylight. At high latitudes, darkness can suddenly gather color. Pale green curtains stretch across the sky, fold into arcs, brighten, fade, and return in new shapes. Red light may appear higher above them, while violet and blue flicker near their lower edges. These displays are auroras, visible signs of energy moving from the sun into Earth's magnetic environment. They seem quiet from the ground, but they are produced by particles traveling through space at great speed, guided by magnetic fields and accelerated through regions far above the atmosphere. An aurora begins with solar activity, though not every display requires a major eruption. The solar wind flows continuously from the sun, carrying charged particles and magnetic fields past Earth. Most of this flow is diverted around the planet by the magnetosphere, the broad region controlled by Earth's own magnetic field. The day side is compressed by the wind, while the night side is stretched into a long magnetotail. This shape is never fixed. It expands, contracts, twists, and stores energy as solar conditions change. When the magnetic field carried by the solar wind aligns in a favorable direction, it can connect with Earth's field through magnetic reconnection. Energy then enters the magnetosphere more efficiently. Particles already trapped within the system are redirected and accelerated, especially through the magnetotail. Some travel along magnetic field lines toward the polar regions, where the field dips into the upper atmosphere. There, the particles collide with atoms and molecules of oxygen and nitrogen. The collisions transfer energy, lifting the atmospheric particles into excited states. When they return to lower energy states, they release light. The color depends on the kind of gas, the energy of the collision, and the altitude at which it occurs. Green auroras are commonly produced by oxygen at heights, where the atmosphere is thin but still dense enough for frequent collisions. Red oxygen emissions usually occur higher, where excited atoms can remain undisturbed long enough to release lower energy light. Nitrogen contributes blue, violet, and reddish tones, often near the lower edges of active displays. The sky becomes a broad natural detector, translating invisible particle motion into color. Auroras usually form rings around the magnetic poles rather than directly above the geographic poles. These oval regions shift with solar wind pressure and magnetic activity. During quiet conditions, they remain concentrated at high latitudes. During stronger disturbances, the ovals expand toward lower latitudes, allowing auroras to appear in places where they are rarely seen. The northern display is called the aurora borealis, while the southern display is called the aurora australis. They are parts of the same global response, though their shapes are not always exact mirrors. The beauty of an aurora can make the event seem harmless, but the same energy transfer may disturb the near-Earth environment on a much larger scale. A strong solar storm often begins with an eruption such as a coronal mass ejection. As the cloud of magnetized plasma crosses interplanetary space, it may interact with earlier solar wind streams, accelerate, slow, compress, or change shape. Forecasting its arrival is difficult because measurements are limited between the Sun and Earth. Observatories can see the eruption leave the corona and estimate its direction and speed, but the magnetic orientation within the cloud is often uncertain until the disturbance reaches monitoring spacecraft positioned upstream from Earth. That orientation strongly affects the storm. If the arriving field points in a direction that reconnects efficiently with Earth's field, the magnetosphere can receive a large amount of energy. The magnetotail stretches, currents intensify, and stored energy is released through substorms and broader geomagnetic activity. Charged particles pour toward the atmosphere, brightening auroras and expanding them toward lower latitudes. At the same time, electrical currents strengthen in the ionosphere, a region of the upper atmosphere containing charged particles created by solar radiation and particle impacts. These currents alter magnetic fields at the surface and can induce currents in long conductors below. Power lines, pipelines, rail systems, and undersea cables can all respond to rapidly changing magnetic conditions. In electrical grids, geomagnetically induced currents may flow through transformers that are designed for ordinary alternating current rather than slow external disturbances. The result can be overheating, voltage instability, equipment damage, or, in severe cases, broad power disruption. The risk depends on the storm, the grid, the ground, and the orientation of power lines. High-latitude regions often face greater exposure, but strong storms can reach farther. Technology in orbit is even more directly affected. Satellites operate above much of the atmosphere's protection, and within regions where energetic particles are common. Solar particles can interfere with electronics, change stored information, damage solar panels, and degrade instruments. Increased radiation can force spacecraft into protective modes. Navigation signals may become less accurate because the ionosphere changes the speed and path of radio waves passing through it. High-frequency radio may be absorbed or redirected during solar disturbances. Polar flights can face communication problems and increased radiation exposure, leading aircraft to change altitude or route. Astronauts beyond the strongest protection of Earth's atmosphere face a more serious biological concern. Energetic particles can pass through tissue and damage cells. Spacecraft shielding reduces exposure, but powerful solar particle events remain a major challenge for long missions outside low Earth orbit. The atmosphere also responds by expanding when ultraviolet and X-ray radiation from solar activity heat its upper layers. A swollen upper atmosphere increases drag on satellites in low orbit. Their paths can decay faster than expected, and operators may need to adjust them. Small satellites with limited propulsion are especially vulnerable. During intense storms, changes in drag can affect many spacecraft at once, complicating tracking and increasing the risk of orbital uncertainty. These effects reveal that Earth's upper atmosphere is not a fixed boundary. It breathes in response to solar energy, expanding during active periods and contracting when conditions quiet. The Sun can disturb modern systems, but its storms also play a long role in planetary history. Solar particles and ultraviolet radiation interact with upper atmospheres, contributing to chemical change and atmospheric escape. On Earth, gravity, the atmosphere, and the magnetic field limit this loss. Mars offers a different example. Its global magnetic field disappeared early, leaving much of the atmosphere more exposed to the solar wind. Spacecraft measurements show that solar storms can increase the rate at which particles escape from the Martian atmosphere. Over deep time, such loss contributes to the transformation of Mars from a wetter world with a thicker atmosphere into the cold, thin-aired planet seen today. A magnetic field alone does not guarantee atmospheric survival, since gravity, chemistry, and replenishment also matter. Yet stellar activity remains part of a planet's long environmental history. Earth's magnetic field is often described as a shield, but it is better understood as a dynamic filter. It deflects much of the solar wind, traps some particles, guides others toward the poles, and sometimes stores energy that is later released. Without the atmosphere, the magnetic field alone would not protect the surface from all radiation. Life benefits from several layers working together. Distance weakens the sun's most intense effects. The magnetosphere redirects charged particles. The atmosphere absorbs dangerous radiation and stops most incoming particles before they reach the ground. Ozone blocks much ultraviolet light. The surface and oceans provide further shelter. Beneath these layers, ecosystems experience solar storms mainly through changes in the sky and, in the technological age, through the systems built above and across the planet. Scientific observation now follows the sun from many locations. Spacecraft monitor the solar wind. Solar telescopes map active regions and magnetic fields. Instruments measure X-rays, ultraviolet radiation, energetic particles, and coronal eruptions. Ground stations and satellites track the response of Earth's magnetic environment. Forecasts cannot remove uncertainty, but they can provide warnings that allow operators to protect spacecraft, adjust power systems, and prepare communication networks. Space weather becomes the study of how solar activity moves through space and affects planetary environments. Conditions change, storms arrive, and quiet returns, but their source lies across the distance between Earth and a star. Auroras are the most visible part of this connection. Their moving light marks the boundary where solar energy, planetary magnetism, and atmospheric gas meet. The same event can be graceful in the sky and disruptive in technology. It can illuminate polar darkness while currents build silently through wires and plasma. Beauty and danger do not arrive as separate forces. They are different expressions of one transfer of energy. The sun awakens life with steady light, but it also reminds that the relationship is active, variable, and never entirely gentle. In the coloured night, Earth reveals both its exposure and its protection, glowing where the solar wind touches the edge of the living world. The sun appears constant across a human lifetime, rising with familiar brightness and holding the planets in paths that seem permanent, yet the star is changing even now. Deep in its core, hydrogen is steadily becoming helium, and the balance that keeps the sun stable is slowly adjusting to that change. The process is so gradual that no generation can feel it directly, but across geological time its effects accumulate. As helium gathers in the center, the core becomes denser and hotter. Fusion in the surrounding hydrogen proceeds more rapidly, and the sun's overall luminosity increases. The star that first warmed the young Earth is dimmer than the star shining in the present age, and the future sun will be brighter still. This slow brightening places a limit on the long habitability of Earth, even before the sun reaches the dramatic final stages of its life. Over hundreds of millions of years, greater solar energy will alter the climate. The carbon cycle may at first reduce atmospheric carbon dioxide as weathering accelerates, helping the planet resist warming. Yet this protection cannot continue forever. Plants that depend on high carbon dioxide levels will face increasing difficulty. Ocean evaporation will strengthen. More water vapor will enter the atmosphere, trapping additional heat. Eventually, the climate may cross thresholds that no geological feedback can reverse. The oceans will begin to shrink, and the surface will become hostile to complex life. Microorganisms may persist longer in sheltered places, beneath the ground or at high latitudes. But even these refuges will fade as heat and water loss continue. The sun therefore ends Earth's living era gradually, not through one sudden event. The same steady increase that once supports warm oceans slowly removes them. Several billion years from now, the core will contain too little hydrogen for the present form of fusion to continue there. Gravity will then compress the helium-rich center, heating it further, while hydrogen fusion shifts into a shell surrounding the core. The outer layers will respond by expanding. The sun will leave the long main sequence stage and become a red giant. Its surface will cool compared with the present photosphere, giving the star a redder appearance. But its total energy output will rise because the expanded surface will be enormous. The inner solar system will be transformed. Mercury is expected to be engulfed. Venus is also likely to disappear within the swollen outer layers. Earth's fate is less certain. As the sun loses mass through powerful winds, its gravitational pull will weaken, allowing planetary orbits to move outward. At the same time, tidal interactions with the expanded solar atmosphere may draw Earth inward. Models differ in their details, and the final outcome depends on processes that are difficult to calculate precisely across such immense spans. Earth may be engulfed, or it may narrowly avoid the outer surface. In either case, the planet will no longer resemble a living world. Its oceans and atmosphere will already be gone, its rocks altered by extreme heat, and its surface reduced to a dry remnant circling a giant star. The red giant phase will not remain stable. The contracting helium core will continue heating until helium nuclei begin to fuse. Because the core is extremely dense, the onset may be rapid in an event known as the helium flash. This release occurs inside the star and does not destroy it. Afterward, the sun will settle for a time into a new balance, fusing helium into carbon and oxygen in the core while hydrogen continues to burn in a surrounding shell. This stage will be far shorter than the long hydrogen burning life. Helium provides less available fuel, and the reactions proceed under hotter conditions. The star will pass through further expansions and contractions as its internal sources of energy shift. Eventually, the core helium will also be exhausted. The sun does not contain enough mass to reach the temperatures required to fuse carbon into much heavier elements. Larger stars continue through additional stages and may end in supernova explosions. But the sun follows a quieter path. Its core becomes a dense mixture composed mainly of carbon and oxygen, while fusion continues intermittently in shells around it. The outer layers expand again, and the star enters an unstable late phase. Pulsations and powerful winds carry material away into space. The sun will lose a large fraction of its mass, releasing gas enriched by the products of its internal reactions. These expanding layers may glow as a planetary nebula, a luminous shell illuminated by the hot exposed core. The name is historical and does not mean that planets are being formed. From a distant system, the dying sun may appear surrounded by delicate arcs, rings, or irregular clouds shaped by magnetic fields, rotation, companions, and uneven mass loss. The display will be brief by stellar standards, lasting only tens of thousands of years before the gas disperses into interstellar space. At the center will remain a white dwarf. This object will contain much of the former core compressed into a sphere roughly comparable in size to Earth. It will no longer produce energy through ordinary fusion. Instead, it will be supported against further collapse by a quantum effect known as electron degeneracy pressure. Electrons resist being forced into identical states, and this resistance holds the compact star against gravity. The white dwarf will begin extremely hot, shining with stored thermal energy, but it will have no continuing fuel source. Over immense time, it will cool and fade. The surrounding planets and smaller bodies will inhabit a system radically altered by mass loss. Their orbits will widen. Some objects may be destabilized as gravitational relationships change. Asteroids and comets may be scattered inward or expelled. The distant remnants of the solar system could continue circling the white dwarf for spans far longer than the age of the present universe. The final cooling toward a dark, cold remnant would take so long that no black dwarf is expected to exist yet. The universe is not old enough for any white dwarf to have cooled completely. The sun's ending therefore stretches beyond all familiar measures of time. The material cast away during the red giant phases will not simply vanish. It will mix with the interstellar medium, joining gas and dust between stars. Some of it may later become part of new clouds, new stars, or new planets. The carbon and oxygen created inside the sun may enter structures that do not yet exist. In this sense, the star returns altered matter to the galaxy, continuing the cycle from which it once formed. The sun itself contains heavier elements inherited from older stars that lived and died before the solar system began. Iron in Earth's rocks, calcium in bones, and carbon in living tissue come from earlier generations of stellar activity. The solar system is already built from recycled cosmic material. Its future dispersal continues the same ancient exchange. The finite life of the sun does not lessen its role as a giver of life. It defines the interval in which that role is possible. Stability is never absolute. It is a long pause between formation and change, long enough for oceans to gather, continents to move, atmospheres to evolve, and simple cells to become forests, animals, and minds capable of tracing their origin to a star. The sun does not awaken life through perfect gentleness. It sends ultraviolet radiation, charged particles, flares, and storms. Its brightness changes slowly, and its eventual expansion will erase the conditions it once maintained. Yet within the middle span of its life, energy arrives with remarkable steadiness. Gravity holds Earth near that flow. The atmosphere filters it. Oceans distribute it. Photosynthesis stores it. Evolution explores the possibilities opened by it. Every living system exists inside this temporary balance. A leaf unfolds because light remains available. A migration begins because the seasons return. Oxygen fills the air because ancient cells learn to use sunlight. Warm oceans persist because the planet receives enough energy, but not yet too much. The present sun is therefore neither eternal nor fleeting. It belongs to a scale between moments and cosmic endings, stable across civilizations but changing across worlds. Far in the future, its light will redden, its outer layers will drift away, and a white dwarf will remain in a silent, widened system. Long before then, Earth's living chapter will close. For now, the star continues its measured transformation of hydrogen into helium, sending energy outward through layered plasma and across space. Dawn follows night, seasons turn, and life continues beneath a light whose beginning and ending are both written into the physics of the sun.